Have you ever looked up at the night sky and felt a sense of overwhelming wonder, only to be hit by a strange, almost unsettling thought? What if the universe is far weirder than our wildest science fiction? We're taught about planets and stars, rockets and orbits, but the real story of space exploration is filled with events so bizarre, so utterly unexpected, that they challenge everything we think we know. It's a realm where common sense takes a backseat and the laws of physics seem to enjoy a good puzzle. Today, we're not just talking about the milestones you learned in school. We're diving deep into the hidden corners of our cosmic journey, into the secrets that are equal parts bewildering and brilliant. This is the side of space that rarely makes the headlines, a collection of mysteries and marvels that prove truth is often stranger than fiction. We are about to embark on a voyage through 30 of the most peculiar and fascinating facts ever discovered through our quest to reach the stars. Each one is a testament to human ingenuity and the sheer strangeness of the cosmos. Imagine a silent, empty glove tumbling through the void, lost by an astronaut and orbiting the Earth for months. Picture a planet where it rains glass sideways, with winds so fierce they could shred a spaceship in an instant. These aren't scenes from a movie, they are real, documented moments in the history of space exploration. These stories aren't just footnotes, they are powerful reminders that every time we push the boundaries of the known, we are guaranteed to find something that will leave us in a state of awe. This journey is a celebration of that curiosity, of the relentless human spirit that looks into the infinite black and dares to ask, what's really out there? So get comfortable and prepare to have your perspective shifted. We're going to explore forgotten artifacts adrift in the void, scientific anomalies that baffled the brightest minds, and cosmic phenomena that defy easy explanation. This is more than a list. It's an invitation to rediscover the magic and mystery of spaceflight, to see the familiar story of rockets and moon landings in a completely new, wonderfully weird light. From the very first satellite to the latest probes on the edge of our solar system, the path of exploration is littered with incredible oddities, and together we're going to uncover them. Let's begin our countdown of 30 weird and wonderful facts about space exploration, starting with a story of a simple, everyday object that achieved the impossible dream of flight in the most unexpected way. And our journey into the bizarre begins not with a distant star or an alien planet, but with the human body itself undergoing a transformation straight out of a science fiction novel. Astronauts who venture into space actually return to Earth taller. That's right, the first of our weird and wonderful facts is that you can grow taller in space, sometimes by as much as 2 full inches. This isn't a magic trick or an illusion. It's a direct and fascinating consequence of living in a microgravity environment. Here on Earth, gravity is constantly compressing our spines. Think of your spinal column as a stack of spongy discs separated by vertebrae. All day, every day, the force of gravity pushes down on this stack, squeezing those discs together. But in the weightlessness of space, that constant compressive force vanishes. For the first time in their lives, the spines of astronauts are free to expand. The vertebrae separate, the spinal discs, which are mostly fluid, can relax and plump up, and the entire column gently stretches out. It's a bit like finally taking a heavy backpack off after a long hike, allowing your body to return to its natural, uncompressed state. Only in space, the backpack of gravity is removed entirely. This sudden growth spurt, however, comes with its own set of challenges. Imagine being on a months-long mission aboard the International Space Station. You get used to your new height, floating through the modules, but then the time comes to return home. As the spacecraft re-enters Earth's atmosphere and gravity reasserts its familiar pull, that extra space in your spine begins to compress again. This rapid recompression can be quite painful, often causing significant back pain for returning astronauts. Their muscles, which have adapted to supporting a longer torso in a weightless environment, now have to work much harder to stabilize a spine that is suddenly being squeezed back to its original size. It's a stark reminder that our bodies are perfectly, and sometimes painfully, adapted for life on this planet. The height gain itself is only temporary, typically reversing within a few months of being back on solid ground. But for a short while, these explorers literally have a new perspective, having seen the world from a slightly higher vantage point, both physically and metaphorically. This simple, personal change highlights a profound truth about space exploration. The greatest mysteries we encounter might not be out among the stars, but within ourselves, as we learn how the fundamental forces of the universe shape our very being. If you thought growing taller in space was a strange personal change, wait until you hear about a world where the very ground beneath your feet would be more precious than any treasure ever unearthed on Earth. Our second fact takes us far beyond our solar system to a truly alien and dazzling place, a planet believed to be composed largely of diamond. This isn't a celestial metaphor or an exaggeration. Scientists have strong evidence for the existence of a carbon-rich super-Earth known as 55 Cancri. Located about 40 light-years away, this planet orbits so close to its parent star that its entire year, one complete orbit, flashes by in just 18 hours. To put that incredible speed into perspective, a birthday celebration on this world would happen more than 20 times for every single one of ours. This blistering proximity creates a surface temperature that soars to thousands of degrees, hot enough to liquefy iron and turn rock into a molten sea. The secret to its diamond nature lies in its unique composition. While Earth is rich in oxygen and silicon, forming rocks and sand, 55 Cancri is incredibly dense and packed with carbon. Under the immense gravitational pressure from the planet's own mass, scientists theorize that this carbon has been compressed and crystallized, forming a vast planet-sized diamond. Imagine a world not of mountains and valleys, but of glittering, crystalline structures stretching across a scorching landscape, glowing ominously in the light of its nearby star. It's a vision of both breathtaking beauty and unimaginable hostility. The concept of value becomes almost meaningless when considering such a place. While it's fun to speculate about the astronomical worth of a diamond planet, the practical challenges of even approaching it are insurmountable with our current technology. Any probe we could send would be vaporized long before it could get a sample. This extraordinary discovery does more than just ignite our imaginations with visions of cosmic riches. It fundamentally expands our understanding of planetary diversity. For a long time, we assumed most planets would be somewhat similar to the rocky or gaseous worlds in our own neighborhood. The existence of 55 Cancri shatters that assumption, proving that the universe can forge worlds from the most unexpected materials under the most extreme conditions. It's a powerful reminder that our cosmic backyard, as vast as it is, represents only a tiny fraction of the possibilities. Every weird world we find forces us to reconsider what a planet can be, pushing the boundaries of science and reminding us that the cosmos holds wonders far beyond our current comprehension. This diamond world is a perfect example of how space exploration continually challenges our assumptions, presenting us with realities that are more fantastic than any fiction. Moving from a distant diamond planet to our own celestial companion, we arrive at a fact that engages a sense we rarely associate with space: smell. After walking on the lunar surface, Apollo astronauts returned to the cramped confines of their lunar module and made a startling discovery. Once they removed their helmets, they were greeted by a peculiar, pungent odor clinging to their suits. They described it consistently as the smell of spent gunpowder or the scent of wet ashes in a fireplace. Think about that for a moment. The moon, a world of profound silence and stark beauty, has a smell, and it's one that feels strangely familiar yet entirely out of place. Archive audio captures astronaut Gene Cernan of Apollo 17, noting how the dust smelled just like someone had fired a carbine in the room. This wasn't a one-off observation. It was a shared experience across multiple missions, a sensory signature of another world brought back inside by the explorers who walked on it. So, what causes this gunpowder-like aroma? The answer lies in the unique nature of the lunar soil itself. Unlike Earth sand, which is smoothed and rounded by wind and water over millennia, moon dust is incredibly sharp and jagged. It's the product of billions of years of relentless bombardment by micrometeorites, which act like a tiny, continuous hammer mill, shattering rock into glass-sharp, reactive particles. Furthermore, this dust is constantly bathed in the solar wind, a stream of charged particles from the sun that embeds itself in the dust grains. On the airless moon, these particles are perfectly preserved in a kind of suspended animation. But inside the lunar module, for the first time, they were exposed to a humid, oxygen-rich atmosphere. Scientists believe this sudden exposure causes a chemical reaction, almost like the dust is rusting or oxidizing in a very rapid, superficial way. The smell we perceive as gunpowder is likely the result of these highly reactive compounds on the dust grains finally interacting with oxygen and moisture, releasing that distinctive scent. In a way, the astronauts weren't smelling the moon as it is, but the moon as it reacts with our own environment. It's the aroma of an alien material being awakened after eons of isolation. This strange sensory detail carries a profound significance beyond the initial curiosity. That simple smell represents a direct, tangible connection to an alien environment, a piece of the moon that could be experienced in a deeply human way, not just through instruments or cameras. It also highlights a very real and unexpected challenge for future lunar exploration. That fine, abrasive, and chemically active dust got into everything, clogging equipment mechanisms, scratching helmet visors, and even causing temporary lunar hay fever in the astronauts. As we plan for longer stays and even a permanent presence on the moon, managing this pervasive and reactive dust will be a critical engineering hurdle. The smell of gunpowder, therefore, is more than a quirky anecdote. It's a sensory warning and a reminder that even the most familiar-looking landscapes in our sky hold alien properties that will test our ingenuity at every turn. While the moon's smell offered a surprising sensory connection to an alien world, our next fact confronts us with a profound and almost unnerving absence: the complete and utter silence of space. In the vacuum that fills the cosmos, there is no sound. Not a whisper, not a rumble, not even the faintest echo. This isn't just a quiet place, it is the definition of silence itself. The reason is fundamental to how sound works. Here on Earth, sound travels in waves that need a medium to move through, like air or water. These molecules bump into each other, creating a chain reaction that carries the vibration to our ears. But space is mostly a perfect vacuum, an emptiness where molecules are so few and far between that they simply cannot collide to propagate a sound wave. A star can explode with the energy of a billion suns, but the colossal shockwave of light and radiation will travel for millions of years in absolute silence. This scientific reality completely upends one of the most dramatic staples of science fiction, the space battle. The iconic roar of a starship's engine, the thunderous blast of laser cannons, the deafening kaboom of an exploding dreadnought, none of it would happen. In reality, a dogfight between spacecraft would be a breathtakingly serene and terrifyingly mute ballet of light. You would see the brilliant flashes of engines and weapons fire. You would feel the vibrations through your ship's hull if a laser beam struck nearby, but your ears would hear nothing at all. It's a disorienting thought, stripping away the visceral intensity we've come to expect and replacing it with a cold, sterile observation. The chaos of combat would be reduced to a silent, panoramic light show, making the event somehow more vast, more distant, and infinitely more eerie. For astronauts, this profound silence is a defining part of the extravehicular experience, or spacewalk. floating outside the International Space Station, with the entirety of planet Earth suspended below them in a majestic swirl of blue and white. They are enveloped in this absolute quiet. The only sounds they perceive are the ones generated internally within their own suit, the rhythmic inhale and exhale of their own breathing, the hum of the suit's life support systems, and occasionally the conduction of vibrations, like when they tap a tool against the station's hull. The sound travels up their arm and through their helmet. This creates a powerful and intimate sensory divide. They are witnessing the most grand and dynamic spectacle imaginable, a world of hurricanes, volcanoes, and sprawling civilizations, yet it all unfolds in perfect, majestic silence. It's a humbling reminder that the universe, in all its violent beauty and grandeur, operates on a scale that often transcends human senses. The silence of space isn't an emptiness. It's a different kind of presence, one that speaks not to our ears, but directly to our sense of awe and our place in the cosmos. While the profound silence of space speaks to the vast scales of the cosmos, our own solar system holds worlds that defy our most basic expectations of time itself. If you ever find yourself planning a trip to Venus, you would need to completely rethink your calendar, because on that cloud-shrouded world, a single day lasts longer than an entire year. This isn't a trick of wording or perspective. It is a literal, mind-bending fact of celestial mechanics. Venus takes a sluggish 243 Earth days to complete one full rotation on its axis. That is the definition of its day, the time from one sunrise to the next. Yet, this same planet races around the Sun in a much briefer 225 Earth days. So, if you were standing on the scorching surface of Venus, the Sun would rise, move across the sky, and set only once for every time the planet completed its journey around our star. Your birthday would arrive before your day was even over. This bizarre situation is caused by Venus's incredibly slow and peculiar spin. Not only is it the slowest rotator of all the major planets, but it also spins in the opposite direction to almost every other planet in our solar system, a characteristic known as retrograde rotation. On Venus, the Sun would rise in the west and set in the east. The leading theory for this backward motion suggests that in the chaotic early days of the solar system, a colossal impact with another large object essentially knocked Venus upside down, setting it spinning the wrong way. Over billions of years, the gravitational tides from the Sun, combined with the crushing, thick atmosphere, have acted like a brake, steadily slowing its rotation to the glacial pace we observe today. Imagine the planet's spin being gradually sapped by the immense friction of its own soupy, superheated air, a global atmosphere so dense it behaves more like an ocean than a sky. The consequences of this slow spin are as dramatic as they are strange. A Venusian day is not just long, it creates an environment of extreme temperature contrast. The surface bakes under a continuous blast of solar radiation for what would be equivalent to months on Earth, with temperatures hot enough to melt lead, hovering around 870 degrees Celsius. Then it plunges into an equally long, frigid night, though the planet's thick carbon dioxide atmosphere acts like a stifling blanket, trapping so much heat that the night side never truly cools down to what we would consider cold. This creates a world of oppressive, uniform heat where the difference between day and night is minimal, but the journey of the Sun across the sky is an achingly slow crawl. For any future robotic lander that might survive more than a few hours on that hellish surface, a single full day-night cycle would represent an immense challenge, having to endure the brutal conditions for the length of an entire Earth year. The weird chronology of Venus serves as a powerful reminder that the rules we take for granted on our own world are not universal laws, but merely local customs in an infinitely varied cosmos. After contemplating the disorienting silence of a Venusian day, we now turn to a discovery that proves the cosmos isn't just a collection of strange worlds, but also a vast and surprisingly well-stocked chemical laboratory. Drifting near the center of our Milky Way galaxy is an interstellar cloud of almost unimaginable proportions, and it holds within it a staggering secret: billions upon billions of liters of alcohol. This is Sagittarius B2, a giant molecular cloud located about 26,000 light-years from Earth, and it is one of the most peculiar reservoirs of organic material ever identified. The specific type of alcohol found in abundance here is vinyl alcohol, which might not be the kind you'd find at a party, but its existence in such vast quantities is a scientific marvel that has profound implications for the origins of life itself. Now, before you start dreaming of a cosmic distillery, it's important to understand that this isn't a cloud of vodka or whiskey floating in the void. Vinyl alcohol is what chemists call a prebiotic molecule, an unstable compound that is considered a direct precursor to more complex organic materials. On Earth, it's not something you would ever encounter naturally in a stable form, but in the cold, low-pressure environment of deep space, these molecules can form and persist on the surface of tiny dust grains. The presence of such an immense cloud of vinyl alcohol is like finding a warehouse full of unassembled parts for a car. It contains the fundamental carbon-based structures that, under the right conditions, could eventually lead to the formation of amino acids and sugars, the very building blocks of life. This cloud, along with others like it, demonstrates that the raw ingredients for biology are not unique to Earth but are scattered abundantly throughout the galaxy, woven into the fabric of star-forming regions. So, how do we even know this cloud exists? We can't see it with optical telescopes as it's shrouded in cosmic dust. Instead, scientists use the power of radio astronomy. Every molecule in the universe has a unique fingerprint. It vibrates and rotates at specific frequencies, emitting faint signals in the radio part of the electromagnetic spectrum. Giant radio telescopes, like the ones at the Alma Observatory in Chile, are like incredibly sensitive ears tuned to listen for these molecular whispers. They scan the dark clouds near the galactic center, and by analyzing the precise frequencies of the radiation they receive, astronomers can identify the chemical signatures of specific molecules, just like a barcode scanner identifies a product. It was through this meticulous spectral analysis that the unmistakable signature of vinyl alcohol was detected in Sagittarius B2, revealing its staggering abundance. The scale of this discovery is what truly bends the mind. The cloud itself is vast, spanning many light years across, and the amount of vinyl alcohol it contains is estimated to be equivalent to 10 to the power of 28 liters. That's a 1 followed by 28 zeros. To put that number into a context that is simultaneously understandable and utterly meaningless, it's more than enough alcohol to fill every ocean on Earth countless times over. This highlights a central theme in modern astrochemistry. The universe is not only capable of creating complex organic molecules, but it does so on an industrial galactic scale. The existence of Sagittarius B2 suggests that the processes that led to the chemistry of life on our own planet are not a rare accident, but a common and ongoing phenomenon wherever stars and planets are born. This giant cloud of alcohol isn't just a weird fact, it's a fragrant hint, a piece of evidence that the universe may be inherently predisposed to creating the conditions for life. The incredible longevity of human footsteps on the Moon stands as one of the most poetic and enduring legacies of our first voyages to another world. Unlike the fleeting marks we leave on a sandy beach, washed away by the very next tide, the footprints made by the Apollo astronauts are not just temporary impressions. They are, for all intents and purposes, permanent historical monuments on a geological timescale. The reason for their incredible persistence boils down to one fundamental difference between the Earth and the Moon: the complete and total absence of an atmosphere. Our planet is a dynamic, living world constantly reshaped by the forces of weather. Wind sweeps across deserts, shifting sand dunes and smoothing surfaces. Rain falls, carving canyons and washing away the smallest traces of life. Even the oxygen in our air slowly breaks down rocks through oxidation. On the Moon, none of these erosive forces exist. There is no wind to gently blow the fine lunar dust, no water to dissolve or displace it, and no biological activity to churn the soil. It is a world frozen in time where any disturbance once made can remain virtually unchanged for eons. The primary agent of change on the lunar surface is an incredibly slow and random process, the rain of micrometeorites. These are tiny specks of cosmic dust, often smaller than a grain of sand, that constantly pelt the Moon. Without an atmosphere to burn them up as they do in brilliant shooting stars on Earth, they strike the surface at tremendous speeds. Over millions of years, this gentle, persistent sandblasting will eventually grind down rocks and, yes, very slowly erase footprints. But this is not a process measured in years or even centuries. It unfolds over millions of years. To understand this timescale, imagine a single footprint on a vast, silent plain. The chance of a micrometeorite hitting that exact spot is astronomically low. The erosion that occurs is a statistical process, a gradual smoothing that happens particle by particle across the entire landscape. The iconic images of Buzz Aldrin's bootprint with its crisp, clear tread pattern will likely remain visible to any future lunar visitors for far longer than human civilization has existed. This fact transforms the lunar surface from a mere landscape into a profound archaeological site. Those footprints are not just marks in the dirt, they are a frozen moment in time, a testament to a specific day when humanity reached beyond its cradle. They are accompanied by other artifacts of incredible permanence: the descent stages of the lunar modules, the scientific instruments of the Apollo Lunar Surface Experiments package, and even the lunar rovers, all sitting exactly where they were left, silently gathering cosmic dust. Because there is no whether to rust or rot them, these machines are preserved in a near-perfect state, apart from the extreme temperature swings between sunlight and shadow, which cause gradual material fatigue. They are a museum exhibition curated not by humans, but by the vacuum of space itself. Contemplating these eternal footprints forces a shift in perspective about our place in the cosmos. On Earth, our monuments, pyramids, skyscrapers, great cities are all temporary when viewed against the backdrop of deep time. They will all eventually succumb to the relentless forces of nature. But on the airless Moon, the evidence of our first tentative steps has been granted a form of immortality. It's a humbling thought that long after our great-grandchildren's great-grandchildren are gone, the marks of those 12 individuals who walked on the lunar surface will still be there, a silent, enduring message to the universe that we were here and that we dared to venture into the great unknown. This permanence makes the Moon a unique historical archive, one that will preserve the tangible evidence of humanity's first off-world exploration for millions of years to come. Leaving behind the timeless footprints on our own Moon, we venture to the outer reaches of our solar system, to a world where volcanoes defy every expectation. On Neptune's largest moon, Triton, the mountains don't spew fire and lava, they erupt with ice. This is the bizarre reality of cryovolcanism, our eighth weird and wonderful fact. Imagine a landscape where geysers blast towering plumes of nitrogen gas and dark dust particles several miles high into an incredibly thin atmosphere, where the erupting material isn't molten rock, but a frigid slurry of water, ammonia, or methane that freezes solid the moment it touches the bitterly cold surface. The average temperature on Triton hovers around -235 degrees Celsius, so cold that even nitrogen exists as a solid ice. Yet somehow, this frozen world displays unmistakable signs of geological activity. The energy driving these icy eruptions doesn't come from the radioactive decay of a hot core as it does on Earth. Instead, Triton is heated from the outside in through a process known as tidal heating. Triton is locked in a gravitational dance with its giant parent planet, Neptune. But this dance is an unusual and strained one because Triton orbits in the opposite direction to Neptune's rotation, a retrograde orbit that is a major clue to its origin. This backward path creates intense and changing gravitational stresses. As Triton moves along its orbit, Neptune's immense gravity constantly stretches and squeezes the Moon's interior, much like repeatedly flexing a piece of metal until it becomes hot. This internal friction generates enough heat to melt the ices deep underground, creating reservoirs of slushy, liquid nitrogen or water that, under pressure, eventually find a weak spot in the surface ice and erupt into the void. This peculiar orbit strongly suggests that Triton was not born alongside Neptune. Astronomers believe it was once an independent object, similar to Pluto, orbiting the Sun in the distant, icy Kuiper belt. Billions of years ago, it strayed too close to the Neptune system, and the planet's gravity captured it, pulling it into its strange, backwards orbit. This violent capture event would have generated tremendous heat, melting its interior and perhaps setting the stage for the geological activity we see today. The Voyager 2 spacecraft, which flew past Neptune in 1989, provided our only close-up images of this alien moon, revealing a young, remarkably smooth surface with very few impact craters, clear evidence that something is constantly resurfacing the terrain, painting over the scars of asteroid impact. The pictures showed dark, streaky deposits fanning out from what are believed to be cryovolcanic vents, stains left by those incredible geysers of nitrogen and dust. Triton stands as a stunning example of how geological wonders are not confined to warm, rocky worlds. It challenges our very definition of a volcano, proving that even in the deepest freeze of the outer solar system, worlds can be dynamic and alive, powered by the subtle but persistent forces of gravity. The prospect of these silent, cold eruptions continuing in the dim sunlight, over 3 billion miles from Earth, expands our understanding of where we might someday look for the ingredients of life, as liquid water, even if buried deep beneath an icy shell, is a key prerequisite. This frozen, erupting moon is a testament to the dynamic and surprising nature of our cosmic neighborhood, a place where even captured wanderers from the icy depths can host some of the most spectacular sights imaginable. After exploring the cold fury of ice volcanoes on Triton, we turn our attention to a far more intimate and human experience, one that reveals just how deeply the laws of physics can dictate even our most fundamental emotions. In the weightlessness of space, you cannot cry, at least not in the way we understand it here on Earth. The simple, cathartic act of shedding a tear becomes a strange and physically complex event. On our planet, gravity is the unseen director of this emotional release. When we cry, tears are produced by our lacrimal glands, and gravity immediately pulls the liquid downward, creating the familiar streams that trace paths down our cheeks. This process is so ingrained in our experience that we never give it a second thought. But in the microgravity environment of the International Space Station, that director is absent. The tears have no force pulling them down. Instead of falling, they simply pool up around the eyeball, clinging to the surface through surface tension. The result is both fascinating and unsettling. As more tears are produced, they gather into a growing, wobbling bubble of liquid that completely covers the eye. Astronauts like Chris Hadfield have famously demonstrated this phenomenon, showing how a large, perfectly formed globule of water can sit directly on the cornea, blurring vision and creating a bizarre liquid lens. If the astronaut continues to produce tears, this bubble grows larger and larger until it eventually detaches, not falling, but floating away as a shimmering, free-floating sphere of salt water. It's a stark, physical manifestation of emotion that is completely detached from the body, a tear that literally takes on a life of its own in the cabin air. While this might sound like a curious party trick, it presents genuine challenges. That floating ball of saline isn't just water, It contains oils and proteins that can irritate the eye if it's not carefully wiped away, and a free-floating liquid sphere in an environment filled with sensitive electronics is something the crew is trained to manage carefully. Beyond the physics, this peculiarity touches on the profound psychological experience of living in space. Crying is a primal, physical release valve for stress, sadness, or even overwhelming joy. The act of wiping away a tear is a comforting, grounding gesture. In space, that entire ritual is upended. The emotion is still there, but the physical expression is altered, becoming something that requires management rather than offering release. The tear doesn't leave you, it clings to you or floats ominously nearby, a constant, visible reminder of the feeling that caused it. For astronauts on long-duration missions, far from family and facing immense pressure, the inability to have a normal cry could, in its own small way, add to the sense of isolation. It's another example of how the human body and its ingrained responses are perfectly tailored for a gravity-based world, and how spaceflight requires adapting not just technologically, but emotionally and physically to a new set of rules. This leads to a broader necessity for emotional resilience. Astronauts undergo years of psychological screening and training to prepare for the mental rigors of spaceflight. They develop coping mechanisms that are less reliant on physical catharsis and more on communication, mindfulness, and the support of their crewmates who become a surrogate family. The weird fact about not being able to cry properly is more than a biological curiosity. It's a window into the holistic challenge of space exploration. It underscores that venturing into this new frontier isn't just about building better rockets or more robust spacesuits. It's about understanding and supporting the fragile, emotional human being inside that suit, who still needs to find a way to express what it feels like to gaze upon the infinite blackness of space or the breathtaking beauty of home from afar. And from the deeply personal experience of crying in space, we shift our gaze to a storm of such immense scale that it makes every hurricane on Earth look like a gentle breeze. Jupiter's Great Red Spot is a colossal, swirling tempest that has been a dominant feature of the solar system's largest planet for centuries, a storm so vast that our entire world could comfortably fit inside it. But this ancient meteorological titan is undergoing a profound transformation. It is shrinking. For at least 400 years since astronomers first trained their primitive telescopes on Jupiter, this great red eye has stared back at them. Yet, detailed observations over the past century, and especially from spacecraft like Voyager and the Hubble Space Telescope, reveal a clear and consistent trend: the storm is getting smaller. The rate of change is dramatic. In the late 19th century, the spot was wide enough to swallow 3 Earths side by side. Today, it's still an unimaginably giant storm, but it's only about 1 Earth in diameter. This slow, steady contraction presents one of the greatest puzzles in planetary science, forcing us to question our understanding of the forces that power and sustain weather on a gas giant. What could be causing this centuries-old storm to gradually wind down? Scientists have proposed several compelling theories. One leading idea points to smaller, swirling eddies and storms that constantly buffet the periphery of the Great Red Spot. Think of the Jovian atmosphere as a chaotic ocean of clouds and gases, with countless smaller whirlpools and jet streams zipping around. As these smaller vortices interact with the edges of the giant storm, they could be acting like a kind of atmospheric sandpaper, gradually eroding its momentum and stealing energy from the main circulation. Another possibility involves changes deep within Jupiter itself. We often forget that what we see is just the cloud tops. The planet is a deep ball of hydrogen and helium with no solid surface. The Great Red Spot is like the tip of an immense, swirling vortex that may extend hundreds of kilometers down into the interior. A shift in the internal heat flow or the dynamics of these deeper layers could be starving the storm of its primary energy source, causing it to slowly weaken and contract from below. The most compelling evidence for this shrinkage comes from a celestial time lapse. captured over decades by the unblinking eye of the Hubble Space Telescope. Year after year, Hubble has taken incredibly sharp portraits of Jupiter, and when these images are stitched together, they tell a silent but powerful story. We can watch as the iconic oval of the storm becomes progressively more circular, its edges appearing to tighten and condense. The intense brick red color that gives the spot its name has also been changing, becoming a deeper, more concentrated hue, perhaps as the storm's winds intensify within a smaller area. These observations are crucial because they provide a long-term, consistent dataset that ground-based telescopes, which have to peer through Earth's turbulent atmosphere, can't match. Hubble gives us a front-row seat to the slow-motion evolution of a world that is utterly alien to our own. The fate of the Great Red Spot is more than just an academic curiosity. It's a key to unlocking the secrets of gas giant planets, not just in our solar system, but across the galaxy. This storm is a natural laboratory for studying fluid dynamics on a scale we could never replicate. Its longevity has always been a mystery, what keeps a storm raging for hundreds of years. Its shrinking forces us to ask the opposite question: what makes it stop? Understanding this process could reveal fundamental truths about how energy is transferred and dissipated in planetary atmospheres. If the Great Red Spot continues to shrink, will it eventually vanish entirely, or will it stabilize at a new, smaller size? Some computer models suggest it might dissipate within our lifetimes, while others indicate it could persist for many more decades. Whatever the outcome, we are living in a unique moment in cosmic history, a time when we have the technology to witness and document the transformation of one of the solar system's most iconic and enduring features, a swirling testament to the dynamic and ever-changing nature of the universe. After contemplating the slow dissolution of a storm that could swallow our world, we now turn to a comparison that brings the vastness of the universe strikingly close to home, revealing a secret abundance right under our noses. It is a fact that seems to defy intuition. There are more trees on Earth than there are stars in our entire galaxy. Let that sink in for a moment. Our planet, a tiny blue marble in the cosmos, hosts a staggering 3 trillion trees. Meanwhile, the Milky Way, a colossal spiral of light containing our sun and hundreds of billions of other suns, is estimated to have between 100 and 400 billion stars. Even at the highest estimate for stars and the lowest for trees, our planet's forests outnumber the galaxy's suns by a significant margin. This isn't just a quirky piece of trivia, it's a profound statement about the sheer density and richness of life on our world. The scale of this arboreal census is almost impossible to visualize. Imagine trying to count every single tree across every continent, from the sprawling Amazon rainforest to the solitary bristlecone pine clinging to a windswept mountain ridge. Scientists arrived at this monumental figure, 3 trillion, through a massive undertaking that combined satellite imagery with thousands of hours of ground-level surveys. This number doesn't even include smaller saplings, but focuses on mature trees with trunks above a certain size. To grasp the sheer volume, consider that this translates to roughly 420 trees for every single human being on the planet. Each one of those trees is a complex living organism, engaged in the silent, vital work of photosynthesis, supporting entire ecosystems in its branches and roots. Now look up at the Milky Way on a clear night. That river of stars, which seems infinite to our eyes, represents a collection of suns that, while incomprehensibly large in their own right, is outnumbered by the silent, leafy giants standing guard on our own world. This stunning comparison serves as a powerful corrective to a common perspective. When we think of space, we often think of overwhelming vastness, of emptiness stretching for light years. We can feel small and insignificant against the cosmic backdrop, but this fact flips that narrative on its head. It tells us that significance isn't solely a matter of physical size or distance. The true marvel may not be the sparse distribution of stars across the galactic void, but the incredible concentration of complex, dynamic life in one small corner of that galaxy. Earth is a planet of spectacular density, a world where life has not just taken hold, but has exploded in a riot of biodiversity, with trees forming the fundamental architecture for much of that life. The galaxy is vast but largely empty. Our planet is small but overwhelmingly full. This realization carries an immense weight of responsibility. Those 3 trillion trees are not a static resource. They are a dynamic and vulnerable part of our planet's life support system. They regulate our atmosphere, stabilize our soils, and provide habitats for countless species. Yet, human activity is reducing their number at an alarming rate, with estimates of a net loss of billions of trees each year due to deforestation and land use changes. Understanding that we are the stewards of a forest that outnumbers the stars in our galaxy reframes our relationship with our home. It's a humbling thought that the preservation of this unique, teeming world of life, a world whose richness is literally galactic in scale, rests in our hands. The grandeur of the Milky Way inspires awe, but the quiet abundance of Earth's forests demands a deeper, more protective kind of wonder. Moving from the silent, teeming forests of our own world to the technological marvels we've placed in the void above, we encounter an instrument that has fundamentally changed our vision of the cosmos. The Hubble Space Telescope, our window to the universe, is a masterpiece of engineering with a surprisingly hefty physical presence. This iconic observatory, which has delivered some of the most breathtaking images in human history, weighs about 11,110 kilograms or 24,500 pounds. To put that immense mass into a relatable perspective, it is roughly equivalent to the weight of 2 fully grown adult African elephants. Imagine the sheer bulk and power of those magnificent creatures. Now picture all that mass packaged into a cylindrical spacecraft 13.2 meters long, a delicate giant designed not for the savannah, but for the unforgiving environment of Earth orbit. The challenge of launching such a massive and incredibly delicate object was a monumental feat of engineering. Hubble couldn't just be put on any rocket. It required the unique capabilities of the space shuttle. Nestled carefully in the shuttle's cavernous cargo bay, the telescope was a payload of unparalleled value and fragility. Its primary mirror, ground to a perfection tolerance of 1/10,000th the width of a human hair, had to survive the violent vibrations and tremendous G-forces of launch. Every component, from the fine guidance sensors to the delicate solar arrays, was engineered to withstand this brutal journey. The deployment itself was a ballet of precision. After reaching orbit, the shuttle's robotic arm, a sophisticated piece of machinery in its own right, would gently lift Hubble out of the bay and position it into the void. Astronauts then conducted a series of spacewalks to complete the setup, unfolding its solar panels and opening aperture doors, like carefully unwrapping a priceless gift before setting it adrift. This entire process was a testament to human ingenuity, a carefully choreographed sequence to give humanity a new eye in the sky. But the true wonder of Hubble lies not in its weight, but in its breathtaking precision once operational. Floating 547 kilometers above the Earth, free from the distorting effects of our atmosphere, this 10.5-ton instrument can lock onto a target with the steadiness of a laser. It has the ability to remain fixed on a single, distant point in the sky for up to 24 hours at a time, with an accuracy equivalent to holding a laser beam steady on a coin over 200 miles away. This incredible stability is what allows it to collect the faint light from galaxies billions of light-years distant, building up an image photon by photon over long exposures. The data it gathers is a form of time travel, allowing us to peer back into the early history of the universe, witnessing the birth of stars and the collisions of galaxies that occurred long before our planet even formed. The footage of Hubble nestled in the shuttle's cargo bay provides a powerful sense of scale, showing this brilliant white cylinder against the vastness of space and the technological might of the shuttle. It appears both immense and strangely vulnerable, a human creation poised on the edge of infinity. That this hefty package of mirrors, electronics, and insulation could be transformed into the most famous telescope in history is a story of ambition and perseverance, especially considering its initial flaw and the daring shuttle missions that followed to correct its vision. The Hubble Space Telescope stands as a symbol that our greatest explorations are not always about sending humans to new worlds, but often about sending our senses, our curiosity, and our intellect out into the cosmos, using tools of immense sophistication to ask the most profound questions about our place in the universe. While the silence of space is absolute, that doesn't mean the objects within it are mute. They simply sing in a language we had to learn how to hear. Our 13th fact reveals a cosmic secret. The sun, the heart of our solar system, produces a deep, resonant hum. This isn't a sound in the traditional sense, as those pressure waves have no air to travel through. Instead, the entire sun is constantly vibrating, pulsing like a colossal bell. The surface of our star is a seething ocean of superheated plasma, and within this churning maelstrom, pressure waves are continuously generated by the turbulent convection below. These waves ricochet through the sun's interior, causing its visible surface to rhythmically rise and fall by tiny amounts, a phenomenon scientists call heliosismology. To translate this celestial music into something our ears can perceive, researchers use a powerful technique known as data sonification. Sophisticated instruments on spacecraft like the Solar and Heliospheric Observatory, or SOHO, meticulously measure the Doppler shift of light across the sun's surface. They track the incredibly subtle motions as areas of the surface move towards us and away from us, blue shifting and red shifting the light with each oscillation. This data, which charts the rise and fall of the solar surface, is essentially a recording of the pressure waves. Scientists then take these wave frequencies and shift them up through 42 octaves into the range of human hearing. What emerges is not a wild cacophony, but a surprisingly soothing, low-frequency drone, a deep and primal note that speaks to the immense forces at work within the star. The sound you hear is a profound low rumble, a bass note so deep it feels more like a physical vibration than a sound. It's the voice of a nuclear furnace, the resonant frequency of a sphere of plasma over 100 times the diameter of Earth. But this hum is far more than just a cosmic curiosity. It is an essential diagnostic tool. Just as geologists use seismic waves from earthquakes to map the interior of our planet, heliophysicists use these solar vibrations to see inside the sun. By studying the patterns in the hum, how long certain waves take to travel through the sun, and how they are shaped by the layers they pass through, scientists can create detailed three-dimensional maps of the star's interior structure. They can determine the temperature, density, and composition of different regions, all from millions of miles away. It's a brilliant example of turning a natural phenomenon into a powerful listening device, allowing us to perform a kind of ultrasound on our parent star. Accompanying this sound, the visuals are equally mesmerizing. Time-lapse imagery from solar observatories shows the sun's surface not as a smooth, solid ball, but as a shimmering, rippling panorama. You can actually see the granules, each one the size of a continent, bubbling and shifting. When these visual ripples are synchronized with the sonified hum, the connection becomes undeniable. You are seeing and hearing the same phenomenon, the rhythmic heartbeat of a living star. This deep, resonant drone is the background music of our solar system, a constant vibration that has been present since the sun ignited over 4.5 billion years ago. It's a hum that fills the space between the planets, a silent song that we have only just learned to listen to, revealing that even in the vacuum, the universe is filled with a vibration that speaks to the dynamic life of the stars. Yet if the sun's deep hum represents the vibrant life of a star, the ultimate fate of some stellar giants leads to a phenomenon of almost unimaginable density. We now venture into the realm of the truly extreme, where the laws of physics are pushed to their absolute limit. Our 14th fact confronts us with a number that challenges all intuition. A single teaspoon of material from a neutron star would weigh billions of tons here on Earth. To grasp the sheer magnitude of that statement, imagine the mass of every car, truck, and building in a sprawling metropolis like New York City. Now compress all of that unimaginable weight into a tiny 5-milliliter spoonful of substance. This isn't science fiction, it is the staggering reality of matter that has undergone the most violent transformation the universe can offer. The creation of a neutron star is a story of cosmic resurrection from stellar death. It begins with a star much more massive than our Sun. For millions of years, this giant burns its nuclear fuel, fighting a constant battle against the immense force of its own gravity. Eventually, the fuel runs out and gravity wins in a single, catastrophic instant. The star's core, no longer supported by the outward push of fusion, collapses in on itself at speeds approaching a quarter of the speed of light. This collapse triggers a titanic rebound explosion known as a supernova, blasting the star's outer layers into space in one of the most energetic events in the cosmos. What remains behind is the crushed, ultra-dense core, a neutron star. In this ultimate act of compression, the very atoms that made up the core are utterly destroyed. The immense gravitational pressure is so overwhelming that it forces the positively charged protons and negatively charged electrons to merge, cancelling their charges and transforming into neutrons. The entire star is effectively turned into a gigantic atomic nucleus, a city-sized ball of solid nuclear material. This is where the incredible density comes from. Under normal circumstances, an atom is almost entirely empty space. If you could magnify a hydrogen atom to the size of a cathedral, the nucleus would be no larger than a grain of sand in the center, with the electron a speck whirling somewhere in the vast dome. In a neutron star, that emptiness is completely eliminated. The gravitational collapse is so powerful that it squeezes out the empty space, pushing the atomic nuclei so close together that they are literally touching. The entire structure is supported not by chemical bonds, but by a quantum mechanical principle known as neutron degeneracy pressure, which prevents the neutrons from being compressed any further. The result is a material that is denser than any substance we could ever create in a laboratory. A single sugar cube made of neutron star material would have a mass roughly equivalent to the entire human population of the Earth, all packed into a space you could balance on your fingertip. The properties of such an object are as bizarre as its density. A neutron star's gravity is so intense that if you were to drop a marshmallow onto its surface from a height of just 1 meter, it would impact with the energy of 1,000 hydrogen bombs. The surface is thought to be a crystalline crust of iron nuclei 10 billion times stronger than steel, floating on an ocean of superfluid neutrons. These stars also spin at phenomenal rates, with some rotating hundreds of times per second, their magnetic fields trillions of times stronger than Earth's, making them the universe's ultimate natural laboratories for testing the most extreme physics. Contemplating a neutron star forces us to abandon all earthly notions of solidity and weight, revealing a universe where matter can exist in states so alien that they defy simple comprehension. It is a humbling reminder that the familiar world of solids, liquids, and gases represents only a tiny fraction of the possible forms that reality can take. After exploring the crushing densities of stellar remnants, we turn to a form of propulsion that is almost ethereal in its elegance, proving that sometimes the most powerful forces are also the gentlest. There is a spacecraft flying right now that is powered not by fiery rocket fuel, but by light itself. This is NASA Light Sail 2, a small, bread loaf-sized satellite that navigates the void using a truly ancient principle, sailing. But instead of catching the wind, it harnesses the subtle, constant pressure of photons streaming from the sun. Imagine a vessel so advanced that its engine requires no fuel tanks, no complex machinery, just a vast, thin, reflective sail that billows not with air but with pure sunlight. It's a concept that sounds like it's straight out of science fiction, yet it's a functioning reality in orbit around our planet, demonstrating a technology that could one day carry probes on epic journeys across the solar system and beyond. The principle behind this incredible feat is known as solar sailing, and it relies on a phenomenon we don't often notice in our daily lives. Light exerts pressure. Although individual photons have no mass, they do carry momentum. When these tiny packets of light strike a surface, they impart a minuscule push. On Earth, this force is so incredibly weak that it's completely undetectable, utterly overwhelmed by gravity and atmospheric pressure. But in the frictionless vacuum of space, where there is no air resistance to counter it, this gentle nudge can accumulate. Given a large enough sail and enough time, the continuous pressure from sunlight can propel a spacecraft to remarkable speeds. It's a bit like trying to push a massive ship with your hand while it's in dry dock. You wouldn't be able to move it an inch, but if that same ship were floating freely in the water, even the slightest, most persistent push would eventually set it in motion. In space, solar sails are that ship, and sunlight is that persistent push. The key to making this work is the sail itself. Light Sail 2's sail is a masterpiece of modern materials science. Stored for launch in a container about the size of a shoebox, it unfurls in orbit to reveal a shimmering square of mylar, an incredibly thin but durable polymer, spanning 32 square meters, roughly the size of a boxing ring. This mylar is thinner than a human hair and incredibly reflective, like a gigantic cosmic balloon. The reflectivity is crucial. For maximum thrust, you want the photons to bounce off the sail, much like a tennis ball bouncing off a racket. With each bounce, the photon transfers more of its momentum to the sail, providing a stronger push than if it were simply absorbed. To steer this light-powered vessel, the entire spacecraft rotates, changing the angle of the sail relative to the sun, just as a sailor trims the sails of a boat to catch the wind from different directions. By angling the sail correctly, controllers can actually use this photon pressure to raise the spacecraft's orbit, a delicate and continuous maneuver that has been successfully demonstrated by Light Sail 2. The potential of this technology is what truly captures the imagination. Unlike conventional rockets that carry a limited supply of fuel which, once spent, ends the mission, a solar sail has an infinite fuel supply, the sun. It can accelerate continuously for years, even decades, gradually building up speeds that could eventually surpass those of traditional spacecraft. While the initial acceleration is painstakingly slow, the constant thrust means that over an interplanetary distance, a solar sail could ultimately reach velocities that would make it ideal for missions to the outer planets or even for an interstellar precursor mission. Imagine a fleet of small, sail-equipped probes venturing towards Jupiter or Saturn, their journeys funded not by colossal rockets but by the free and endless energy of our star. There are even proposals for giant, ground-based lasers that could beam concentrated light onto sails, pushing them to a significant fraction of the speed of light for voyages to nearby star systems. Light Sail 2 is the humble but profoundly important proof of concept for these grand visions, a small craft that is currently teaching us how to ride the light, opening a new chapter in exploration that is as silent, clean, and elegant as the universe itself. From the gentle, light-powered flight of solar sails, we plunge directly into one of the most counterintuitive discoveries in our solar system. On Mercury, the planet closest to the Sun, where surface temperatures on the sunlit side can soar to 430 degrees Celsius, hot enough to melt lead, astronomers have found something astonishing: vast deposits of water ice. This discovery defies every logical assumption about a world that basks in such intense solar radiation. The secret to this frozen water's survival lies not in its proximity to the sun, but in a simple yet profound feature of Mercury's geography and celestial mechanics, its craters. Unlike Earth, which has a significant axial tilt that gives us our seasons, Mercury's rotational axis is almost perfectly perpendicular to its orbit. This means the planet has no real seasons to speak of, and it creates a unique phenomenon at its poles. The rims of certain craters near the north and south poles cast permanent, unyielding shadows across their floors, creating pockets of eternal night in a world of endless day. Inside these deep polar craters, the conditions are more akin to the frozen depths of the outer solar system than to a scorching inner planet. Without ever receiving a single ray of sunlight, the temperatures in these shadowed abysses plummet to a bone-chilling -200°C. At these extreme lows, water ice is not just stable, it can persist for billions of years, effectively acting as a natural deep freeze. The idea that such frigid sanctuaries could exist just a short distance from some of the most hellish surface conditions in the solar system is a testament to the complex and surprising nature of planetary environments. It's a dramatic illustration of how local topography can create microclimates that are wildly different from the global average, offering a safe haven for volatile materials that would otherwise instantly vanish. The first compelling evidence for this ice came not from optical telescopes, which obviously cannot see into permanent darkness, but from the powerful Arecibo radio telescope in the 1990s. Scientists aimed a beam of radar waves at Mercury's polar regions. When those waves bounced back, they revealed something extraordinary: patches with an unusually high radar reflectivity, appearing brilliantly white in the radar images. This specific signature is a classic indicator of water ice. The crystalline structure of ice reflects radar signals in a very distinctive way, much brighter than rocky surfaces. It was a eureka, a moment suggesting that something other than rock was hiding in those shadows. This initial discovery was later confirmed and mapped in exquisite detail by NASA, a messenger spacecraft, which went into orbit around Mercury in 2011. Messenger neutron spectrometer detected a telltale signal of hydrogen, a key component of water, concentrated exactly in those permanently shadowed craters. Some of these ice deposits are estimated to be several meters thick, and in total, they may contain billions of tons of water ice. The existence of this ice forces a fundamental rethink about the delivery of water throughout the solar system. How did water get to a place like Mercury? The leading theory points to a cosmic delivery service that has been operating for eons: comets and water-rich asteroids. Over the history of the solar system, these icy wanderers have bombarded every planet. When one impacts Mercury, the tremendous heat of the collision would vaporize most of the comet's ice instantly. But a fraction of that water vapor could be launched across the planet's surface. Some molecules would randomly bounce into the polar regions, and if their trajectory took them into a permanently shadowed crater, they would instantly freeze and become trapped, accumulating layer by layer over billions of years. This same process is thought to have played a role in delivering water to Earth and the Moon, suggesting a common cosmic source for this most vital of resources. The implications of this discovery reach far beyond scientific curiosity. For future human exploration, water ice is not just for drinking. It can be split into hydrogen and oxygen to create breathable air and, crucially, rocket fuel. The presence of accessible ice on Mercury and in similar permanently shadowed craters on the Moon transforms these worlds from mere destinations into potential stepping stones. They could one day serve as interplanetary refueling stations, making the solar system more accessible. The discovery of ice on Mercury shatters our simplistic view of the inner solar system as a dry, barren wasteland. It reveals a dynamic history of bombardment and preservation, and it proves that even in the most unlikely places, the ingredients for life can find a way to endure, hidden in the shadows, waiting to tell their story. While the silent hum of the sun speaks to the life of a star, the human body responds to the absence of gravity with its own quiet, internal changes, particularly within the very rhythm that defines our existence. Astronauts experience a significant and fascinating physiological adaptation. Their heartbeats slow down in space. On Earth, our cardiovascular system is in a constant battle with gravity. Every time you stand up, your heart has to work a little harder to push blood upward to your brain against the planet's relentless pull. It's a struggle we're so accustomed to we never even notice it, but it means that even at complete rest, our hearts maintain a certain baseline level of effort. In the weightlessness of microgravity, that fundamental challenge simply vanishes. The blood in your body is no longer pooling in your legs, it distributes itself evenly, and your heart no longer needs to fight an uphill battle. As a result, it can relax and the resting heart rate drops. This change isn't minor, it's a substantial shift that reflects the body's remarkable ability to adapt to a new environment. An astronaut who might have a typical resting heart rate of around 60 to 70 beats per minute on Earth could see that number fall into the 40s or 50s while living on the International Space Station. Imagine the heart, that tireless muscle, finally getting a chance to ease its pace after a lifetime of constant exertion. This is one of the most immediate and measurable signs of the body acclimating to spaceflight. The cardiovascular system, in essence, becomes more efficient, requiring fewer beats to circulate the same amount of blood when it doesn't have to contend with gravity's downward drag. For a short time, this might seem like a beneficial vacation for the heart. However, this adaptation comes with a significant catch, one that reveals a profound truth about human physiology. Our bodies are built for stress. The heart is a muscle, and like any muscle, it needs regular, challenging work to stay strong. In the same way that an athlete's heart rate lowers because their heart is more powerful and efficient, the astronaut's lower rate in space is initially a sign of efficiency. But without the constant gravity-induced stress, the heart muscle can begin to atrophy, weakening over time. This is why exercise is not just a recommendation aboard the ISS. It is a non-negotiable, critical part of the daily routine, a medical prescription for survival. Astronauts are required to spend at least 2 hours each day vigorously exercising using specialized equipment like treadmills with harnesses that simulate weight and advanced resistance machines. This rigorous regimen is designed to artificially stress the cardiovascular system, tricking the body into thinking it still needs to work hard, thereby preventing the heart from weakening and ensuring it remains strong enough for the return to Earth's gravity. The data that tracks this entire process is visually compelling and tells a clear story of adaptation and readaptation. If you were to look at a graph of an astronaut's average resting heart rate across a 6-month mission, you would likely see a distinct curve. At the beginning of the mission, the rate plummets sharply as the body quickly responds to the novel environment of microgravity. It then stabilizes at this new, lower plateau for the duration of the stay. The most critical part of the graph comes at the end, after the astronaut returns to Earth. The heart rate doesn't just snap back to its pre-flight normal, it often spikes significantly higher than it was before the mission began. This is the heart struggling, a clear sign of deconditioning. It's now suddenly tasked with a job it hasn't had to do for months fighting gravity, and it's weaker for the experience. It can take weeks or even months of rehabilitation back on the ground for the heart to regain its former strength and for the resting rate to return to its baseline. This simple line on a graph encapsulates the entire human experience of spaceflight: the rapid adaptation to a new reality, the sustained effort to maintain health in an alien environment, and the challenging, often painful process of coming home. It's a powerful reminder that even our most fundamental rhythms are shaped by the world we live in, and when we step off that world, we must actively fight to preserve the very body that carries us. While the discovery of ice on Mercury revealed hidden resources in the most unexpected places, Our next destination showcases a geological wonder on a scale so grand it redefines our very concept of a mountain. Behold Olympus Mons, the largest volcano in the solar system, a colossal feature on Mars that makes even the mightiest peaks on Earth look like mere foothills. To truly grasp its immensity, picture this. Olympus Mons stands approximately 16 miles high, which is about 25 kilometers from its base to its summit. That is nearly 2.5 times the height of Mount Everest when measured from sea level. But its most staggering characteristic is its footprint. This volcano is so wide it covers an area roughly the size of the entire state of Arizona. If you were standing on its outer edge, the peak would be so far away and the slope so gradual that it would be hidden beyond the curvature of the Martian horizon. It is not so much a mountain you climb, but a vast, sloping plain you would traverse, unaware you are even ascending one of the solar system's greatest titans. The secret to Olympus Mons' staggering size lies in a fundamental difference between Mars and Earth: the absence of plate tectonics. Our planet is a dynamic, shifting jigsaw puzzle of crustal plates that are constantly moving over a molten mantle. This movement has a crucial limiting effect on volcanoes. On Earth, as a hotspot in the mantle feeds magma to the surface, the overlying tectonic plate slowly drifts sideways. This creates a chain of volcanoes like the Hawaiian Islands, where each volcano is born, grows for a while, and then is carried away from its magma source, becoming extinct. No single volcano is given the chance to grow indefinitely. Mars, however, is a one-plate planet. Its crust is a single, stationary lid. This means that for billions of years, a fixed hotspot beneath the Tharsis region, where Olympus Mons is located, has been pumping magma directly to the same spot on the surface. Without any tectonic motion to shift it away, the volcano just kept growing and growing, layer upon layer of lava flow after lava flow, accumulating into the monumental structure we see today. Visualizing this behemoth requires more than just numbers. It demands a perspective that only global maps and detailed three-dimensional renderings can provide. When you look at a global image of Mars, Olympus Mons is an unmissable feature, a massive, dark blotch near the equator, surrounded by a steep cliff that in some places is as tall as 6 kilometers, a sheer face that would dwarf any canyon on Earth. Zooming in with satellite imagery reveals a complex caldera at its summit, a collapsed area about 80 kilometers wide, a chaotic pit that could swallow entire cities. This isn't a single crater, but a nested set of several calderas formed by different eruptive episodes, a testament to the volcano's long and active history. Three-dimensional models that tilt the landscape provide the most dramatic sense of scale, showing how the volcano's gentle slopes, with an average incline of only 5 degrees, belie its truly monstrous proportions. You could drive a car up those slopes and barely notice the ascent, yet the journey to the top would be longer than a road trip across several states. The implications of such a massive geological feature are profound. Olympus Mons is not just a record holder, it is a frozen chronicle of Martian history. Its immense size suggests that Mars was once a far more volcanically active world than it is today, with a much thicker atmosphere and possibly even conditions suitable for liquid water on its surface. The lava flows that built Olympus Mons would have released vast quantities of gases, helping to shape the ancient Martian climate. While the volcano is believed to be dormant now, its very existence challenges our understanding of planetary evolution. It stands as a silent, monumental reminder of the powerful forces that shaped the rocky worlds of our solar system, and a humbling indicator that the geological processes we are familiar with on Earth are merely one variation on a theme that can play out on a much grander scale elsewhere. This sprawling monument on Mars highlights the quiet, geological forces that can shape a world over billions of years. But the environment immediately surrounding our own planet is becoming shaped by a much more recent and worrying force: our own discarded technology. The space around Earth is no longer a pristine void. It is cluttered with a swirling shell of debris, a growing constellation of human-made junk that poses a serious threat to our future in space. This isn't just a few lost tools. We're talking about an estimated 1 million pieces of debris larger than a centimeter across, all racing around the planet at speeds exceeding 17,000 miles per hour. This cloud includes everything from defunct satellites the size of a school bus to spent rocket stages, flecks of paint, and even the iconic lost glove from that first American spacewalk, each one a potential bullet in the orbital shooting gallery. The sheer velocity of this debris is what makes even the smallest object so dangerous. At orbital speeds, a chip of paint may seem insignificant, but its kinetic energy is colossal. Imagine a single marble, but traveling 10 times faster than a bullet fired from a high-powered rifle. A collision with an object that small could shatter a window on the International Space Station or disable a critical satellite. The danger isn't merely theoretical, it's a daily operational concern. The International Space Station has to perform regular debris avoidance maneuvers, firing its thrusters to shift its orbit and dodge a piece of tracked debris several times a year. These are unplanned, fuel-consuming maneuvers that highlight the very real and present danger this junk cloud represents to human lives and vital infrastructure. This situation becomes exponentially more terrifying when we consider a theoretical tipping point known as the Kessler syndrome. Proposed by NASA scientist Donald Kessler in the 1970s, this scenario outlines a catastrophic chain reaction. Imagine one large, derelict satellite colliding with another. That single impact wouldn't just create two pieces of debris, it would shatter them into thousands of new fragments, each now a projectile in its own right. These new pieces then increase the probability of hitting other objects, leading to more collisions which create even more debris, and so on. In a worst-case scenario, this cascade could create an impassable barrier of shrapnel in certain orbits, effectively trapping us on Earth. Certain valuable orbits, like the low Earth orbit used by the ISS and many Earth observation satellites, could become so congested with fast-moving junk that it would be too risky to launch new missions or maintain existing ones. It would be a slow-motion paralysis of our spacefaring capabilities, a problem of our own making. Recognizing the urgency, scientists and engineers around the world are now actively developing solutions for what is essentially a cosmic cleanup operation. These concepts range from the simple to the science-fictional. Some proposals involve harpoons that would spear larger pieces of debris and then drag them down into the atmosphere where they would safely burn up. Other ideas include using powerful lasers to gently nudge smaller fragments off their collision courses, or massive nets to capture clusters of junk. The European Space Agency is leading the way with missions like Clear Space One, which aims to be the first to capture and remove a piece of existing debris. These are incredibly complex undertakings, requiring a spacecraft to rendezvous with a tumbling, uncooperative object and safely secure it without creating even more fragments in the process. Visualizing this problem is key to understanding its scale. Animations based on real tracking data reveal a startling image. Our planet is enveloped in a dense, buzzing swarm of dots, with the busiest regions looking like a beehive of activity. This digital cloud makes abstract numbers terrifyingly concrete, showing how we have actively created our own obstacle course in space. The efforts to clean it up represent a critical new chapter in space exploration, shifting from pure discovery to active stewardship. It's a responsibility we can no longer ignore, a necessary task to ensure that the pathways to the stars, which we have worked so hard to open, remain clear and safe for the explorers and innovators of tomorrow. The pristine environment of a spacecraft, a marvel of human engineering, might seem like the last place you'd expect to encounter a heightened biological threat. But one of the most insidious challenges of long-duration spaceflight lurks within the astronauts themselves. Our 20th fact reveals a deeply concerning phenomenon. some bacteria become more virulent in space. In the microgravity environment of the International Space Station, common microbes like Salmonella, a frequent cause of food poisoning on Earth, have been observed to transform, becoming significantly more infectious and developing a troubling resistance to antibiotics. This isn't a plot from a thriller novel. It's a documented scientific discovery that has profound implications for the health of crews on their way to the Moon, Mars, and beyond. The initial discovery of this effect was both startling and systematic. In experiments conducted aboard the Space Shuttle and the ISS, scientists sent carefully contained samples of Salmonella into orbit. When these space-traveling bacteria were later injected into mice back on Earth, they were found to be far deadlier, killing the animals much more quickly than control samples that had remained on the ground. The difference was stark and demanded an explanation. The root cause appears to be a combination of factors unique to the space environment, with microgravity playing a leading role. On Earth, gravity influences everything, including how fluids behave around bacterial cells. In microgravity, the physical forces acting on the bacteria change dramatically. This altered environment appears to act as a stressor, triggering a survival response in the microbes. In a sense, the bacteria feel like they are under attack, and their natural reaction is to ramp up their defenses and their ability to cause infection, essentially hunkering down for a fight. Scientists have been able to peer into the mechanics of this transformation, and what they've found is a process called fluid shear. In a laboratory flask on Earth, bacteria are constantly settling due to gravity, creating a gentle churning motion in the liquid around them. In space, this settling doesn't happen. The cells float freely, experiencing a much more tranquil environment. This lack of fluid shear seems to be a key signal that something is different, prompting changes in how the bacteria's genes are expressed. Researchers identified specific changes in the expression of at least 167 genes in the spacefaring Salmonella and pinpointed a master protein called HFQ that acts as a genetic regulator, essentially flipping the switches that make the bacteria more potent. It's a fascinating and admittedly frightening example of rapid evolution in action, all driven by the subtle shift from a gravity-rich to a gravity-free world. The visual evidence of this change is both beautiful and alarming. When you compare microscopic images of Salmonella grown in space to their Earth-bound counterparts, the difference is visible. The space-grown bacteria often form what are known as biofilms, dense, slimy communities that cling to surfaces. These biofilms are a bacterial fortress. They make the microbial community vastly more resilient, protecting the cells within from antibiotics and making them exceedingly difficult to eradicate. Imagine a slimy layer coating a surface inside a spacecraft's water system or air filters, harboring a supercharged version of a familiar pathogen. For astronauts whose immune systems are already compromised by the stresses of spaceflight, this combination presents a serious risk. A simple infection that would be a minor inconvenience on Earth could escalate into a life-threatening crisis millions of miles from the nearest hospital. This discovery fundamentally shifts how we must approach mission planning. Astronaut health has always been a priority, but the threat of enhanced microbial virulence adds a new layer of complexity to planetary protection protocols. But in reverse, it's about protecting the explorers from their own microscopic passengers. It means that future spacecraft and habitats will need to be designed with antimicrobial surfaces and advanced, redundant life support systems that can aggressively manage microbial growth. Medical kits for long-duration missions will need to be stocked with a wider array of antibiotics and perhaps alternative therapies like phage therapy, which uses viruses that specifically target bacteria to stay ahead of potential resistance. Every aspect of hygiene becomes magnified in importance, from food preparation to waste management, because in the confined ecosystem of a spacecraft, there is no room for error. The silent, adaptive evolution of bacteria in space serves as a humbling reminder that as we venture outward, we bring our entire biological reality with us, and some of our smallest companions may prove to be our most formidable opponents. While our planet grapples with a cloud of its own making in near-Earth orbit, a much larger and more profound celestial dance is quietly unfolding, one that will ultimately change the face of our sky. The moon, our constant companion for billions of years, is slowly leaving us. Each year, the moon drifts about 1.5 inches or 3.8 centimeters farther away from Earth. This distance is roughly the same as how much your fingernails grow in a year, a seemingly trivial amount, but when compounded over the immense scales of geological time, it adds up to a dramatic reconfiguration of the Earth-Moon system. The mechanism behind this gradual retreat is a powerful and continuous transfer of energy driven by the familiar tug of the ocean tides. The process begins with the gravitational pull of the moon, which causes the Earth's oceans to bulge outward, creating the high tides we see on our coastlines. However, because the Earth rotates on its axis much faster than the moon orbits around us, our planet's spin actually drags this tidal bulge slightly ahead of the moon. Think of it as a parent spinning in place while holding a child's hand. The child is swung outwards away from the center. This leading bulge of water, in turn, exerts its own gravitational pull on the moon. This extra tug is minuscule, but it acts like a constant, gentle accelerator, giving the moon a tiny boost in its orbit. The fundamental rule of orbital mechanics is that when you add energy to an orbiting body, it moves to a higher, slower orbit. So, with each passing year, this tidal interaction gives the moon a little push, causing it to spiral outward by that 1.5 inches. But this cosmic exchange doesn't come without a cost. The energy that pushes the moon away has to come from somewhere, and it is siphoned directly from the Earth's rotation. This constant gravitational friction acts as a brake on our planet's spin, ever so gradually slowing it down. The result is that the length of an Earth day is increasing. Millions of years ago, a day on Earth was significantly shorter. During the time of the dinosaurs, a day was only about 23 hours long. This slowing is incredibly gradual, adding about 1.7 milliseconds to the length of a day per century. It's a change utterly imperceptible in a human lifetime, but over hundreds of millions of years, it has a profound effect. This is the same principle that has already locked other moons in our solar system into synchronous rotation, meaning they show the same face to their planet, just as our moon does with Earth. The Earth-Moon system is evolving toward a similar, distant future state. One of the most beautiful and direct consequences of this slow-moving drift concerns one of nature's most spectacular events, the total solar eclipse. The magic of a perfect total eclipse hinges on a celestial coincidence that feels almost too good to be true. The sun is about 400 times larger than the moon, but it also happens to be about 400 times farther away. This perfect alignment of scale and distance means that from our vantage point on Earth, the moon and the sun appear to be almost exactly the same size in the sky. This is why during a total eclipse, the moon can just barely cover the entire disk of the sun, revealing the delicate, wispy tendrils of the solar corona. But as the moon continues to recede, its apparent size in our sky will steadily shrink. In about 600 million years, the moon will have drifted far enough away that it will no longer be able to completely cover the sun. The era of total solar eclipses will come to an end. Future inhabitants of Earth, if there are any, will only ever see annular or ring of fire eclipses, where a brilliant ring of sunlight remains visible around the dark silhouette of the moon. The breathtaking totality that has inspired awe, fear, and scientific discovery throughout human history will be gone forever, a transient gift in the planetary timeline. Visualizing this process makes it much clearer. Simple animations can show the Earth rotating rapidly with the tidal bulge pulled ahead by that spin. A line representing the gravitational pull from this bulge can be seen gently tugging the Moon forward in its orbit, causing its path to widen in a slow, graceful spiral. A counter on the screen can tick upward, showing the increasing distance year by year, while another displays the gradually lengthening day. A final, poignant animation could fast forward through time, showing the Moon's disk shrinking in the sky until during an eclipse it fails to cover the Sun, leaving that brilliant ring of light. This slow, inexorable drift is a reminder that the cosmos is not a static museum display but a dynamic, evolving system. The sky we look up to today is not the sky of the distant past, and it will not be the sky of the far future. Our planet and its moon are partners in a slow, graceful ballet, their movements dictated by the fundamental laws of physics, gradually changing the very rhythm of our world and the spectacle of our heavens. But if the slow drift of our moon represents a gentle, predictable change in our celestial neighborhood, the magnificent rings of Saturn present a spectacle of such breathtaking beauty that they appear to be a permanent, eternal feature of the solar system. Yet, one of the most startling discoveries of the modern space age is that they are anything but. The prevailing theory, supported by a wealth of data from the Cassini mission, suggests that Saturn's rings are relative newborns, likely forming a mere 100 to 200 million years ago. To grasp the significance of that age, consider that the solar system itself is 4.5 billion years old. This means that for 95% of the history of our cosmic neighborhood, since the reign of the dinosaurs began and ended, Saturn orbited the Sun as a naked planet, its skies devoid of the glorious, icy halo we see today. The evidence for this youthful age comes from a meticulous analysis of the rings' composition and their interaction with Saturn itself. The Cassini spacecraft, which spent 13 years orbiting the gas giant, provided incredibly precise measurements. One key finding was the purity of the ring ice. Saturn's rings are overwhelmingly made of water ice, and they are remarkably bright and reflective. If they were as ancient as the solar system, they should have been darkened over billions of years by a constant rain of micrometeoritic dust from interplanetary space. The fact that they are still so pristine suggests they haven't been exposed to this cosmic pollution for very long. Furthermore, Cassini was able to measure the mass of the rings by observing how its trajectory was minutely altered by the ring's gravitational pull. This revealed that the rings are far less massive than if they were primordial. Their relative lightness points to a recent origin, a single, dramatic event rather than a slow, gradual accumulation over eons. So what cataclysm could have created such splendor so recently? The leading hypothesis is a violent and beautiful accident. The theory suggests that Saturn's gravity captured a wandering object, perhaps a large, icy moon that strayed too close, or a comet from the distant Kuiper belt. The immense tidal forces exerted by the planet would have torn this visitor apart, shredding it into countless fragments. Imagine a world of ice, perhaps larger than the dwarf planet Pluto, being unraveled like a ball of yarn by Saturn's gravity. The debris from this destruction, caught in the planet's gravitational grip, would have quickly spread out into a disk. Within this disk, particles collided and coalesced, their orbits circularizing over time through countless collisions, eventually settling into the thin, orderly bands we observe today. It's a creation story born from destruction, where the death of a single celestial body gave birth to the solar system's most iconic landmark. The visual legacy of the Cassini mission allows us to witness this delicate structure in stunning detail. Its images are not just photographs, they are scientific documents that reveal the ring's dynamic nature. We can see incredible intricacies, braided rings, spoke-like features that appear and disappear, and sharp edges maintained by the gravitational nudges of tiny, shepherd moons orbiting within the ring system itself. These visuals show the rings not as a static painting, but as a living, evolving system, a cosmic laboratory where physics plays out on an unimaginable scale. The rings are incredibly thin, in some places no thicker than a 3-story building, yet they stretch over 280,000 kilometers in diameter. This exquisite flatness is a testament to the constant collisions between particles, smoothing out any irregularities, a process that would have taken far less than 100 million years to achieve. The youth of Saturn's rings forces a profound shift in our perspective. We often look at the solar system as a finished product, a clockwork mechanism that has been ticking steadily since its formation. The existence of such a recent and spectacular feature reminds us that our cosmic neighborhood is still a dynamic and sometimes violent place. Major events that reshape worlds can happen on a timescale that, while vast by human standards, is a mere blink of an eye in geological terms. It also makes our own era feel uniquely special. The great dinosaurs never saw Saturn's rings. Early mammals scurrying underfoot in the age after the asteroid impact did not see them. Humanity, in its infancy, looked up and was the first intelligent life on Earth to witness this glorious crown around the 6th planet. This realization imbues the rings with a new kind of magic. They are not a permanent fixture but a temporary wonder, a celestial gift that graces our particular moment in the long history of the solar system, a reminder that the cosmos is still capable of creating breathtaking beauty from chaos. While Saturn's rings stand as a monument to recent cosmic violence, the quest to find other worlds like our own has revealed a universe that is not just beautiful but astonishingly prolific. The Kepler Space Telescope, a mission dedicated to planet hunting, has given us a number that fundamentally reshapes our place in the cosmos. There are probably more than 20 billion Earth-like planets in our galaxy alone. This is not a wild guess or science fiction. It is a statistical conclusion drawn from years of meticulous observation, and it suggests that planets capable of hosting conditions similar to our own are the rule, not the exception. Kepler's primary mission was to stare relentlessly at a single, small patch of sky near the constellations Cygnus and Lyra, monitoring the brightness of over 150,000 stars for the telltale sign of a planet crossing in front of its sun, a tiny, periodic dip in starlight known as a transit. From this vast and continuous dataset, scientists could perform a kind of cosmic census. They weren't trying to find every single planet in the galaxy. They were finding a representative sample in one region to extrapolate the total population. The math behind this is both straightforward and staggering. Kepler discovered thousands of planets, and from that data, astronomers calculated that a significant percentage of stars in our galaxy host planets, a concept known as the planet occurrence rate. More specifically, they found that a substantial fraction of those planets are rocky, terrestrial worlds like Earth, Mars, and Venus, and that a further percentage of those rocky worlds orbit within their star's habitable zone. This Goldilocks zone is the orbital distance where conditions are just right, not too hot and not too cold for liquid water to potentially exist on the surface, a key ingredient for life as we know it. When you take the estimated number of stars in the Milky Way, which is between 100 and 400 billion, and apply these percentages, the result is a conservative estimate of at least 20 billion worlds with a basic potential for Earth-like conditions. But what does Earth-like really mean in this context? It's crucial to understand that this term is used in a specific geological sense rather than a guarantee of a tropical paradise. An Earth-like or Earth-sized planet, as defined by these surveys, is primarily a world with a similar radius and mass to our own, implying a rocky composition with a solid surface. It does not necessarily mean the planet has an atmosphere, oceans, or a magnetic field, let alone life. It simply identifies a candidate, a place where the fundamental physical prerequisites for a habitable environment could exist. Many of these worlds orbit red dwarf stars, which are smaller, cooler, and far more common than stars like our Sun. This presents a double-edged sword. While these stars have long lifespans, offering ample time for life to arise, Their habitable zones are so close in that planets within them are likely tidally locked, with one side in perpetual daylight and the other in endless night, creating extreme weather patterns. Others might orbit sun-like stars, offering a more familiar day-night cycle. The term Earth-like is therefore a starting point for imagination, a flag planted on a world of possibilities that invites further, more detailed investigation. To breathe life into these statistical probabilities, artists and scientists collaborate to create stunning concepts of these distant worlds. These illustrations are not wild guesses. They are informed speculations based on the hard data we have: the planet's estimated size, its distance from its star, and the type of star it orbits. We might see a world imagined as a vast desert with a large red sun hanging in a pink sky. Another concept could depict a water world, a planet with little to no land, its entire surface a global ocean beneath a thick, cloudy atmosphere. Yet another might show a pale blue dot strikingly similar to our own, with white cloud swirls and hints of continents orbiting a yellow star. These visuals are powerful because they transform abstract numbers and graphs into tangible, awe-inspiring landscapes. They help us visualize the sheer diversity of environments that might exist among those 20 billion worlds, each one a unique experiment in planetary evolution. This incredible abundance carries a profound philosophical weight. For centuries, humanity has wondered if we are alone, gazing at the stars and questioning our solitude. The data from Kepler provides a powerful, albeit indirect, answer. It suggests that the basic ingredients for a habitable world are commonplace. The processes that formed our solar system, the accretion of dust into planets within a circumstellar disk, are apparently a universal phenomenon. This doesn't prove that life exists elsewhere, but it dramatically improves the odds. It means there are billions of stages upon which the drama of life could potentially be playing out. The universe, it seems, is not a barren wasteland punctuated by the occasional oasis. It is a garden rich with potential, filled with worlds waiting to be discovered. The next great challenge for astronomy is to move from detecting these worlds to characterizing them, using powerful new instruments like the James Webb Space Telescope to analyze the light filtering through their atmospheres, searching for the chemical signatures of water, oxygen, and methane, potential biosignatures that would turn a statistic into a revolution. After contemplating the staggering abundance of potential worlds across the galaxy, we now turn our focus to a record of an entirely different kind, one that exists not in the vastness of space, but within a compact, humming laboratory orbiting high above our heads. The coldest place in the known universe isn't in the dark void between galaxies or on some distant, frozen planet. It is a human-made chamber on the International Space Station. Within a facility called the Cold Atom Lab, scientists routinely create conditions that are 1 billion times colder than the depths of interstellar space, chilling matter to within a fraction of a degree of absolute zero. This isn't just about setting a record. It's about pushing atoms into a bizarre new state of existence, a realm where the familiar rules of physics break down and quantum weirdness takes over. And this research is only possible because it's being done in the weightlessness of orbit. To understand the significance of this achievement, we first need to grasp the concept of absolute zero. Temperature is fundamentally a measure of motion. It's the average kinetic energy of atoms and molecules jiggling and vibrating. The hotter something is, the more its atoms dance around. As you cool matter down, this motion slows. Absolute zero, which is minus 273.15 degrees Celsius or minus 459.67 degrees Fahrenheit, is the theoretical point where all atomic motion ceases entirely. It's the absolute bottom of the temperature scale, a state of perfect, motionless cold. Of course, reaching this perfect standstill is physically impossible, but the scientists at the Cold Atom Lab get astonishingly close, cooling clouds of atoms to within a 10 billionth of a degree above it. At these temperatures, atoms are moving slower than a walking pace, a dramatic contrast to their usual frenetic speeds of thousands of miles per hour at room temperature. The magic happens when atoms are cooled to these extreme lows. They enter a strange and wonderful phase of matter predicted by Satyendra Nath Bose and Albert Einstein a century ago, known as a Bose-Einstein condensate. In this state, individual atoms lose their identity. Their quantum waves, which are usually insignificant, spread out and overlap, causing millions of atoms to sync up and behave as if they were a single, giant superatom. It's like a chaotic crowd of people suddenly moving in perfect, unified lockstep. This collective behavior allows scientists to observe quantum mechanical phenomena, which are typically only visible at the subatomic scale, on a scale large enough to see with specialized instruments. It's a window into the fundamental nature of reality, but there's a catch. On Earth, gravity is the enemy of this delicate state. The incredibly weak force of gravity pulls on these fragile condensates, dragging them down and causing them to collapse within a fraction of a second, giving researchers only a fleeting moment to study them before they vanish. This is precisely why the Cold Atom Lab is located on the International Space Station. Microgravity is the key to unlocking the full potential of this research. In the persistent free fall of orbit, the force of gravity is effectively eliminated for the experiments inside the lab. Without gravity pulling the Bose-Einstein condensate downward, it can be contained by much weaker magnetic fields, allowing it to hold its shape for far longer. Whereas Earth-based experiments might only have a second to make observations on the space station, scientists can maintain and study these condensates for 5 to 10 seconds, and in some cases even longer. This might not sound like much, but it's an eternity in the world of quantum physics. This extended observation time is like having a camera that can suddenly take a 10-second exposure of a firework explosion instead of a blurry snapshot. The resulting image is infinitely clearer and more detailed, revealing intricacies that were previously impossible to see. The process of creating this profound cold is a multi-stage marvel of engineering. Inside the sealed lab, which is about the size of a large mini-fridge, lasers are used to initially slow down a cloud of rubidium or potassium atoms. Think of these lasers as a form of optical molasses, where photons of light act like tiny bullets, hitting the atoms from all directions and sapping their momentum. This first stage cools the atoms to within a few degrees of absolute zero. But to reach the final, ultimate cold, another ingenious technique is employed: evaporative cooling. The warmer, faster-moving atoms are coaxed out of the magnetic trap, much like a cup of hot coffee cools as the most energetic water molecules evaporate away from the surface. The remaining atoms are left with a lower average energy and thus a lower temperature. By carefully repeating this process, the cloud is driven down to temperatures that are almost unimaginable. Visualizing this abstract concept is crucial. Imagine an animation showing a swarm of colorful, buzzing atoms representing a gas at room temperature. As the cooling process begins, the colors shift to cooler blues and purples, and the frantic motion of the atoms visibly slows to a gentle drift. Upon reaching the Bose-Einstein condensate state, the individual atoms merge into a single, glowing, wave-like blob, pulsating with a serene light. To illustrate the advantage of space, a split screen could show the Earth-based condensate quickly sagging and falling out of its trap due to gravity, while the space-based version floats perfectly suspended, stable and observable for a dramatically longer duration. This side-by-side comparison makes the benefit of the space environment immediately clear. The research conducted in this unique laboratory isn't just an academic exercise, it has profound practical implications. By studying the precise behavior of atoms in this state, scientists can refine the technology behind ultra-sensitive quantum sensors. These sensors could lead to dramatic improvements in navigation systems for spacecraft, allowing them to traverse the solar system with unparalleled accuracy without needing GPS. They could also be used to measure tiny variations in gravity, which could help us map the interior of alien worlds or discover hidden underground resources on Earth. The Cold Atom Lab, a box of extreme cold in the vastness of space, is proving to be a hotbed of discovery, pushing the boundaries of our knowledge and paving the way for technologies that will shape the future of exploration. If you thought the slow, graceful drift of our moon was a lesson in celestial patience, then prepare to visit a world where time itself seems to have slowed to a crawl. On the distant dwarf planet Pluto, a single day lasts for 153 hours, which is equivalent to about 6.4 Earth days. Imagine a sunrise that takes the better part of an Earth week to complete, with a single period of daylight stretching on for over 3 full days. This incredibly slow rotation is just the beginning of Pluto's chronological strangeness, a world whose concept of time is dictated by its lonely, elliptical path on the very edge of our solar system. The reason for this drawn-out day lies in the mechanics of its orbit and its relationship with its largest moon, Charon. The two bodies are so close in size that they are gravitationally locked in a cosmic dance, forever facing one another. This mutual tidal locking means that Pluto's rotation has been synced to Charon's orbit, resulting in this 6.5-day cycle. From the surface of Pluto, Charon would not appear to rise or set like our moon does. It would hang motionless in the sky, a gigantic gray companion that dominates the heavens, its features permanently fixed in place. This creates a day that is not defined by a solitary world spinning in isolation, but by a binary system slowly pivoting together through the void. This leisurely spin, however, is only half the story of Pluto's extreme environment. The dwarf planet's axis is tilted at a dramatic angle of about 120 degrees. To put that in perspective, if Earth's 23-degree tilt gives us our mild seasons, Pluto's tilt is so extreme that it essentially rotates on its side. This means that during its 248th Earth year, long orbit around the Sun, entire hemispheres of Pluto experience seasons of unimaginable duration and intensity. For nearly a quarter of its year, over 60 Earth years, one pole is bathed in continuous sunlight, while the other is plunged into a deep, frigid night that lasts just as long. The slow march of these seasons, combined with the long days, means that the surface conditions on Pluto change on a scale that is almost geological. The stunning images sent back by NASA, a New Horizons spacecraft during its historic flyby in 2015, give us a breathtaking glimpse of this complex world. These are not the blurry, pixelated pictures of old textbooks. They reveal a landscape of shocking diversity and beauty. We see vast, heart-shaped plains of nitrogen ice, smooth and relatively young, which have been named Sputnik Planitia. Towering over these plains are mountain ranges of water ice, hard as rock at Pluto's surface temperature of -230 degrees Celsius. The visuals show a world with dark, cratered regions right next to bright, icy plains, suggesting a geologically active body where something, perhaps the slow warming and cooling over its epic seasons, is resurfacing the terrain. The long Plutonian days would create a strange, soft light, with the sun appearing as little more than a very bright star in the perpetual twilight, casting long, slowly moving shadows across this alien, frozen mosaic. The interplay between the long day and the extreme seasons creates a climate system that is unique in our solar system. During the decades-long summer in one hemisphere, the weak sunlight is enough to vaporize the nitrogen ice on the surface, causing it to sublimate directly into a very thin atmosphere. This atmosphere, primarily nitrogen with traces of methane and carbon monoxide, freezes out again completely when that hemisphere swings into its multi-decade winter, collapsing back onto the surface as fresh ice. This seasonal transfer of mass from one pole to the other is a global process that might even affect the planet's rotation over millions of years. The long days mean that each surface region bakes in the feeble sunlight for an extended period, then radiates its heat away into the blackness of space during an equally long night, leading to temperature swings that we can only model from a distance. Contemplating a world like Pluto forces a radical shift in our perspective on time and change. The processes that shape its surface, the sublimation of ices, the flow of glaciers, the creation of its thin atmosphere, unfold over centuries, not seasons. A single storm, if one could exist there, might rage for years. The New Horizons flyby was a snapshot, a single frame in a movie that is overwhelmingly slow by human standards. We saw Pluto at one specific moment in its long year, a moment that will not be repeated for 2.5 centuries. This distant, frozen world, with its week-long days and century-long seasons, stands as a majestic testament to the incredible variety of planetary clocks ticking throughout our solar system, each one keeping time according to its own unique rhythm and place in the cosmos. And from the frozen, slow-moving world of Pluto, we return to a much closer and more personal artifact of exploration, one that has become a symbol of one of humanity's greatest achievements. A question often asked about the Apollo moon landings is a simple but poignant one. What happened to the flags? The 6 American flags planted by the astronauts on the lunar surface between 1969 and 1972 are still there, but if we could see them today, they would almost certainly be unrecognizable. Decades of exposure to the most hostile environment imaginable have likely transformed those iconic symbols into plain, bone-white banners. The vibrant red and blue stripes, the field of white stars, have all probably been bleached away by the relentless, unfiltered fury of the sun. The primary agent of this transformation is solar ultraviolet radiation. Here on Earth, we are protected from the sun's most damaging UV rays by our atmosphere, which acts as a giant protective filter. But the moon has no such shield. The flags have been subjected to a direct, unimpeded bombardment of high-energy UV light for over 50 years. This radiation is incredibly effective at breaking down chemical bonds, especially in the dyes used to color the nylon fabric of the flags. The process is one of photodegradation, where the photons of light carry enough energy to shatter the complex molecules that give the dye its color. Imagine leaving a brightly colored piece of fabric on the roof of a building for half a century, exposed to sun and rain. It would fade significantly. Now multiply that effect by thousands, removing the protection of the atmosphere and the weathering effects of water. The result is a complete and total bleaching. The flags haven't just faded, they have likely been stripped of all color, returning the nylon to its original white state. But the radiation is only part of the story. The extreme temperature swings on the lunar surface have also taken a toll. Each lunar day lasts for about 14 Earth days, with surface temperatures soaring to 127 degrees Celsius. This is followed by an equally long night where the temperature plummets to -173 degrees Celsius. The flags have endured this brutal heating and freezing cycle not just dozens but thousands of times. This thermal cycling causes the fabric to expand and contract repeatedly, making it brittle and fragile over time. Furthermore, the flags were not designed for permanence. To make them appear as if they were flying in the windless vacuum, NASA engineers installed a horizontal crossbar at the top of each flagpole. However, the force of the rocket exhaust from the lunar module's ascent stage when the astronauts departed would have blasted the nearest flags with intense, high-velocity gas. It's believed that the flag planted by the Apollo 11 crew, being closest to the spacecraft, was probably knocked over by this blast. The others, while possibly still standing, would have been subjected to a sandblasting of fine, abrasive lunar dust, further degrading their surfaces. So, what would we see if we could visit the sites today? Conceptual images based on scientific analysis provide a haunting vision. A side-by-side comparison would be striking. On one side, the familiar flag from 1969, its colors bright and bold against the gray lunar soil. On the other, a starkly different object, a white, tattered rectangle perhaps sagging on its pole. The material might be so brittle that it is beginning to disintegrate with tiny micro-tears from the relentless thermal stress and micrometeorite impacts. The symbolic power of these objects undergoes a fascinating shift with this knowledge. They were never intended to be permanent monuments. They were gestures of a specific moment in history. Their transformation from national symbols to universal relics is a powerful metaphor. The colors representing one nation have been washed away by the impersonal forces of the cosmos, leaving behind a simple, white flag that now belongs not to a single country, but to all of humanity, a silent testament to the day we first stepped onto another world. Their bleaching is not a sign of disrespect, but a natural process that has, in a way, elevated their meaning, marking them as true artifacts of the lunar environment, changed by the very world they were planted on. While the ancient, bleached flags on the moon stand as silent monuments to our past visits, a recent discovery has completely reshaped our understanding of our celestial neighbor, turning it from a dusty museum into a potential resource depot for our future. We've long known that water ice could survive in the permanently shadowed craters at the lunar poles, but the idea that water could exist in broad daylight on the sunbathed surface seemed impossible. That is, until NASA, a stratospheric observatory for infrared astronomy, or SOFIA, made a groundbreaking detection confirming the presence of water molecules in a sunlit region for the very first time. The specific location was Clavius Crater, one of the largest and oldest craters visible from Earth through a simple backyard telescope, a vast impact basin near the Moon's southern hemisphere that is fully exposed to the Sun's rays. The reason this discovery was so surprising lies in the Moon's extreme environment. Without a significant atmosphere to regulate temperature, the lunar surface in direct sunlight can reach a scorching 127 degrees Celsius. At such high temperatures, scientists expected any water present to instantly vaporize and be lost to space. The prevailing theory was that water could only be trapped as ice in the perpetual, frigid shadows of polar craters, where temperatures plummet to -200 degrees Celsius. Finding water molecules clinging to a sunlit surface forced a major rethink of lunar chemistry and the processes at work there. Scientists now believe the water might be physically trapped within tiny, glass-like beads created by the intense heat of micrometeorite impacts, or sheltered in the microscopic spaces between lunar soil grains, which could provide just enough shade to prevent immediate sublimation. It's a testament to water's incredible tenacity, finding a way to exist in the most unlikely of niches. The instrument that made this discovery possible is a marvel of ingenuity. SOFIA isn't a typical ground-based telescope. It's a highly modified Boeing 747 SP jetliner that carries a massive 2.7-meter reflecting telescope high into the stratosphere. Flying at altitudes of up to 45,000 feet, SOFIA soars above 99% of the water vapor in Earth's atmosphere. This is crucial because water vapor in our own air absorbs the specific infrared signature that SOFIA was trying to detect on the Moon, effectively blinding ground-based telescopes to this wavelength. By getting above this blanket of vapor, SOFIA telescope had a crystal-clear view of the infrared universe. The key instrument for this observation was its faint object infrared camera for the SOFIA telescope, or forecast, which is exquisitely sensitive to the particular wavelength of light emitted by water molecules, a spectral fingerprint at 6 microns. The data that confirmed the presence of water is a perfect example of how astronomers decode the light from distant objects. When SOFIA pointed forecast at Clavius Crater, it wasn't looking for a puddle or a patch of frost. It was measuring the precise spectrum of infrared light reflecting off the lunar soil. The graph of this data shows a smooth curve, but with a distinct telltale dip at the exact wavelength of 6.0 microns. This dip is the signature of water molecules absorbing the infrared radiation at that specific energy level. It's like a barcode. The presence of that dip is a direct indicator that water is there. The strength of the signal allowed scientists to estimate the abundance, which is about the equivalent of a 12-ounce water bottle trapped within a cubic meter of lunar soil spread across the crater. While this is 100 times drier than the Sahara Desert, the mere fact that it exists in a sunlit area is what makes the discovery so revolutionary. The implications of this finding for the future of lunar exploration cannot be overstated. Up until this point, plans for a sustainable human presence on the Moon, like NASA Artemis program, were heavily reliant on the idea of mining water ice from the permanently shadowed polar craters. These regions are incredibly difficult to access, perpetually dark and bitterly cold. The discovery that water might be more widely distributed across the sunlit surface, even in minuscule amounts, opens up new, more flexible options. If this surface water can be efficiently extracted, it could potentially be used by future astronauts as a vital resource. Water is, of course, essential for life support, for drinking and growing food. But even more critically, it can be split through electrolysis into its component parts, hydrogen and oxygen. Oxygen is needed for breathing, and together, hydrogen and oxygen form a powerful rocket propellant. This means the Moon could potentially offer refueling stations for spacecraft, turning it into a stepping stone for deeper missions to Mars and beyond. The discovery of water on the sunlit Moon transforms it from a mere destination into a potential gas station in the sky, fundamentally changing the economics and logistics of humanity's future in space. Now, if you've ever watched the International Space Station pass overhead on a clear night, appearing as a steady, silent star gliding across the sky, it's almost impossible to comprehend the sheer velocity at which it's actually moving. The ISS is hurtling around our planet at a breathtaking 17,500 miles per hour. To put that incomprehensible speed into a more relatable context, that's about 5 miles every single second. In the time it takes you to read this sentence, the station has traveled the distance from one side of a major city to the other. This isn't just fast, it's a speed necessary for survival, the precise velocity required to achieve a perfect balance between forward momentum and the constant pull of Earth's gravity, a state of perpetual freefall that we call orbit. This incredible speed translates directly into a dizzying pace of life for the astronauts on board. Because the station is moving so quickly, it completes a full lap around the entire Earth once every 90 minutes. This means the crew experiences a sunrise and a sunset roughly every 45 minutes. Imagine the rhythm of that existence, a full 24-hour cycle compressed into just an hour and a half. In a single Earth day, the astronauts witness the sun cresting the horizon 16 times and the planet plunging into night another 16 times. There is no gradual, lingering twilight up there. The transition is abrupt and dramatic. One moment, you are floating beside a window, looking down at a continent bathed in brilliant sunlight, and then, in an instant, you cross the Terminator line. The dividing line between day and night, and the world below vanishes into an inky blackness punctuated only by the glittering clusters of city lights. This constant cycling can be disorienting, which is why the station operates on coordinated universal time, essentially Greenwich Mean Time, to maintain a consistent schedule for work, meals, and sleep, creating a semblance of a normal day despite the celestial carnival ride happening outside the window. The most stunning way to grasp this velocity is through the breathtaking time-lapse footage captured by the astronauts themselves. These videos, often set to stirring music, show the Earth unfurling below at an astonishing rate. You don't see the slow drift of clouds you'd observe from an airplane. You see entire weather systems swirling and evolving in a matter of seconds. The distinct outlines of continents slide by with the swiftness of a map being unrolled. You can watch the jagged, snow-capped spine of the Andes Mountains race past, see the vast, reddish expanse of the Australian outback transform into the intricate coastline of Southeast Asia, and witness the electric glow of human civilization lighting up the night side of the planet like a web of luminous bacteria. The curvature of the Earth is always present, a constant, humbling reminder of the planetary scale on which this journey is taking place. This is not a simulation. This is the actual view from a laboratory moving at 23 times the speed of sound. Living at this pace fundamentally alters an astronaut's perception of our world. The familiar borders and divisions that define life on the surface become invisible from this altitude and speed. There are no lines separating nations, no visible signs of conflict or politics. Instead, the planet reveals itself as a single, integrated, and breathtakingly beautiful system. You see the thin, fragile layer of our atmosphere, a delicate blue haze on the horizon that protects all known life from the harsh vacuum of space. You witness the dance of auroras, the silent, shimmering curtains of light that ripple at the poles. The rapid orbit means no single natural disaster or weather event is hidden for long. A hurricane brewing in the Atlantic, a volcanic plume rising in the Pacific, and the sprawling deforestation in the Amazon all pass by the windows in a single work shift. This perspective, often described as the overview effect, is a profound cognitive shift in awareness reported by many astronauts, a feeling of interconnectedness and responsibility that comes from seeing the entirety of our isolated, fragile world in one sweeping glance over and over again 16 times a day. The incredible speed of the International Space Station, therefore, is not just a technical necessity. It is the engine for a transformative human experience, offering a vantage point that forever changes how we see our place in the cosmos. While the discovery of water on the sunlit moon reshapes our plans for the future, our understanding of the solar system's outer dark is also being rewritten by a ghost, a world that has never been seen, but whose presence is felt through the strange behavior of distant objects. The case for a hypothetical Planet 9 is one of the most compelling detective stories in modern astronomy, built not on a direct photograph, but on a pattern of gravitational whispers echoing from the edge of our cosmic neighborhood. The evidence comes from a specific group of small, icy bodies orbiting far beyond Neptune in a region known as the Kuiper Belt. While most of these objects have orbits that are randomly oriented, a handful of the most distant ones behave bizarrely. Their orbits are clustered together, all tilted in a similar direction, and they all swing out to their most distant point, their aphelion, in the same general region of space. This is astronomically strange. It's as if you threw a handful of marbles onto a large, flat table, and instead of scattering randomly, they all rolled to one specific corner. This peculiar clustering is a telltale sign that something massive is herding them, its gravity sculpting their paths over millions of years. To visualize this, animated diagrams are essential. Picture a standard diagram of our solar system, with the orbits of the 8 known planets circling the Sun. Now zoom out far beyond Neptune into the realm of the Kuiper Belt, shown as a vast, diffused donut of countless icy dots. Among this swarm, a small group of objects is highlighted. At first, their orbits seem chaotic, but as the animation progresses, a pattern emerges. Lines representing their elongated paths all point towards the same distant quadrant of space. The animation then introduces a simple, heavy dot representing the proposed planet 9 on its own vast, elliptical orbit. As this dot slowly moves, its immense gravitational field acts like a shepherd, gently nudging the orbits of the smaller bodies over time, forcing their most distant points to align with its own position. This visual makes the abstract mathematical evidence instantly understandable, showing how an unseen presence can impose order on distant chaos. The proposed characteristics of this hidden world are as staggering as the evidence for it. Based on the gravitational pull needed to create the observed clustering, Planet 9 is estimated to have a mass somewhere between 5 and 10 times that of Earth. This would make it a so-called super-Earth or a mini-Neptune, a type of planet that is common around other stars but is conspicuously absent from our own solar system. Its orbit, however, is anything but common. It's thought to be hugely elliptical, taking it on a tremendously long journey around the Sun that could last between 10,000 and 20,000 years. At its closest approach, it might come within a few hundred astronomical units of the Sun, but at its most distant, it could be well over 1,000 AU away. To put that in perspective, 1 astronomical unit is the distance from the Earth to the Sun. Pluto is only about 40 AU away on average. Planet 9 would be living in a profound and distant twilight, so far from the Sun that it would appear as little more than a bright star in its own sky. The search for this elusive giant is a monumental challenge that pushes the limits of our technology. The main obstacle is its incredible distance and presumed dimness. At such a vast remove, the Sun's light would be tremendously faint, and the amount of sunlight reflecting off the planet back towards Earth would be vanishingly small. Searching for it is like looking for a single, dim light bulb somewhere in the expanse of a large city from an airplane flying overhead at night. Astronomers are using the world's most powerful telescopes, like the Subaru telescope in Hawaii, to meticulously scan the vast stretches of sky where the planet's predicted orbit might lie. They take images of the same patch of sky over several nights, looking for one faint dot that moves just a tiny amount against the background of fixed stars. It's a painstaking, needle-in-a-haystack endeavor that requires immense patience and computational power to analyze the mountains of data generated. The discovery of Planet 9 would be a triumph of indirect detection and celestial mechanics, a reminder that even in an age of advanced technology, some of the universe's biggest secrets are still revealed not by what we see, but by the subtle fingerprints they leave on their surroundings. Yet, for all our incredible advancements in robotics and artificial intelligence, the path to human spaceflight was first blazed not by engineers or astronauts, but by a small, quiet pioneer whose story remains one of the most poignant and complex in the history of exploration. Our final fact takes us back to the very beginning, to a time of fierce political competition and breathtaking scientific risk, when a stray dog plucked from the streets of Moscow became the first living creature to orbit the Earth. Her name was Laika, and her journey aboard Sputnik 2 in 1957 marked a monumental and tragic leap into the unknown, a mission that secured a crucial propaganda victory for the Soviet Union while igniting a global debate on the ethics of sending animals into space. Laika was not a highly trained laboratory animal. She was a mongrel, a 3-year-old stray found wandering the city. Soviet scientists believed stray dogs were ideal candidates because they had already endured the harsh conditions and hunger of life on the streets, making them resilient and hardy. She was a gentle, quiet dog, described as calm and friendly by the team that prepared her. They gave her several names, including Kudryavka or Little Curly, but it was Laika, the Russian word for a barking dog breed, that would echo around the world. Her training was brutal, designed to prepare her for the terrifying ordeal of launch and weightlessness. She was confined in progressively smaller cages for days on end to acclimate her to the tiny cabin of the spacecraft. She was spun in centrifuges to simulate the intense G-forces of rocket acceleration and placed in machines that vibrated violently to mimic the launch itself. Through it all, she endured, her survival instincts and the kindness of the scientists who grew fond of her being her only comforts. The mission of Sputnik 2 was a direct response to the stunning success of Sputnik 1, the first artificial satellite which had shocked the world just a month earlier. Soviet Premier Nikita Khrushchev, eager to maintain the propaganda momentum, demanded another, even more spectacular, space feat to celebrate the 40th anniversary of the Bolshevik Revolution. With virtually no time to design a spacecraft that could return safely to Earth, the engineers were given an impossible deadline. Sputnik 2 was by necessity a one-way ticket. The decision was made from the start that Laika would not survive the journey. The primary goal was to prove that a living organism could withstand the conditions of launch and orbit, a critical step before a human could be sent. The spacecraft was equipped with a life support system, an oxygen generator and a device to absorb carbon dioxide, and sensors to monitor her heartbeat, blood pressure, and breathing. There was a feeding apparatus that provided a gelatinous, nutritious food, but there was no plan for re-entry. On November 3, 1957, Leica was sealed inside her pressurized cabin atop the R-7 rocket. The final photographs taken of her before the hatch was closed show a patient, trusting face, unaware of the history she was about to make. The launch was successful, and as Sputnik 2 entered orbit, the world learned that a dog was circling the planet. For a few hours, data streamed back to Earth, showing that Leica had survived the launch and was coping with weightlessness, albeit with a heart rate 3 times its normal level due to stress. The official Soviet narrative, maintained for decades, was that Leica lived for several days, was euthanized painlessly with poisoned food, and eventually burned up when Sputnik 2 re-entered the atmosphere months later. The truth, however, was far more grim and was not revealed until 2002, when a scientist involved in the mission disclosed the terrible reality. Due to a thermal control system that failed shortly after reaching orbit, the capsule rapidly overheated. Within a few hours, Leica succumbed to heat and stress. Her death was a harrowing end to a brave life. The legacy of Leica's mission is deeply layered. On one hand, it was an undeniable scientific triumph. She proved that a mammal could survive the initial rigors of spaceflight, paving the way for the missions that would eventually carry Yuri Gagarin into orbit. The data collected, however brief, was invaluable. Yet her sacrifice sparked an immediate and powerful ethical debate, particularly in the West. There were public outcries and protests. Newspapers referred to the mission as Mutnik, and editorials questioned the morality of sending a living being on a suicide mission. This public pressure would lead to significant changes in how animal spaceflight was approached, with future missions focusing on designs that included recovery systems. Leica became more than a scientific subject. She became a global symbol. Her story is a stark reminder of the immense costs and difficult choices that underpin humanity's greatest adventures. She was a silent partner in our quest for the stars, a small, courageous dog whose lonely journey forced us to confront the price of progress and to honor the lives, both human and animal, that have been spent reaching for the cosmos. And so, our incredible voyage through 30 of the cosmos's most peculiar secrets comes to an end. From astronauts growing taller to diamond planets, from the silent gunpowder scent of the moon to a humming sun and a sky filled with billions of Earth-like worlds, we have journeyed to the very edges of our understanding and found that reality consistently outshines our wildest imaginations. This collection of facts is far more than a simple list of curiosities. It is a powerful testament to the relentless, surprising, and utterly wondrous nature of discovery itself. Every time we send a probe into the void or train a telescope on a distant galaxy, we are not just confirming what we already know, we are inviting the universe to astonish us, to challenge our most basic assumptions, and to reveal a truth that is infinitely more complex and beautiful than we ever dreamed. This entire journey stands as a monument to human ingenuity. Consider the sheer brilliance required to listen to the vibrations of a star, to deduce the existence of an unseen planet from the subtle dance of icy asteroids, or to design a spacecraft that sails on sunlight. These are not trivial achievements. They are the products of countless minds working across generations, driven by an insatiable curiosity to look into the darkness and ask, what's out there? The weird and the wonderful are not separate from science. They are its very heart. They are the moments when the data doesn't fit, when the image from a probe shows something utterly unexpected, forcing us to go back to the drawing board and rethink the rules of reality. It is in these anomalies that the greatest breakthroughs are born, pushing our technology and our intellect to new heights. As we close this chapter, the adventure is far from over. In fact, it is accelerating. New telescopes peer deeper into the past, and new missions are being prepared for moons with subsurface oceans and asteroids rich with resources. The next 30 weird and wonderful facts are out there, waiting to be uncovered by the next generation of explorers, which includes every single one of you watching. The universe has shown us that it is a place of infinite variety and endless surprise, and our quest to understand it is one of the most noble and exciting endeavors we can undertake. Now we want to hear from you. As you look back on this journey, which fact left you the most awestruck? Was it the eternal footprints on the moon, the shrinking great red spot, or the lonely, brave journey of Leica? Share your favorite moment in the comments below. Let's continue the conversation and marvel together at the strangeness of it all. If you enjoyed this cosmic countdown, make sure to subscribe to the channel and hit the notification bell so you don't miss our next adventure into the mysteries of the universe. Thank you for joining us on this tour of the bizarre and the brilliant. Until next time, keep looking up, keep wondering, and never stop being amazed by the incredible story that is space exploration.